So today's lecture is going to be on reduced rank regression. I want to discuss how it relates to, on the one hand, multivariate linear regression, but also how it relates to canonical correlation analysis, and how all three methods are somewhat related and can be viewed as being within the same framework. And so to start, I just want to quickly review multivariate linear regression so that we have a common setup. So let y1 to yn be a random sample of size n, and let x1 to xn be the corresponding sample of covariates. Here yi will be of dimension p, and xi will be of dimension q. And so we assume a linear relationship between y and x. And so we say the expected value of y given x is equal to b transpose times xi, where B is a Q by P matrix of regression coefficients. We'll write Y bold and X bold for the matrices whose ith row is Yi and Xi respectively. And so this allows us to write the ordinary least squares estimator as follows. And so it's the inverse of X transpose X times X transpose Y. And so this should be familiar because we've discussed multivariate linear regression several lectures ago. And so one thing that we discussed when we talked about linear regression and the least squares estimate is that it's equivalent to p-independent univariate regressions. In other words, it's the same as if we had performed univariate regressions independently. The estimator is not influenced in any way by the correlation between the different components of yi. And so there's no sharing of information across the outcome variables. So that's one key observation. And then the second important observation is that the matrix B itself is Q times P, and so it has P times Q regression coefficients that we need to estimate. So every time we add an outcome variable, we need to estimate Q new parameters. And so we see how it grows pretty quickly. And so this is sort of the motivation for reduced rank regression. So one way to mitigate both effects, or the effect of both observations, is to impose a rank restriction on B. And so instead of having B being full rank, we can make an assumption that B is actually of smaller rank, K. And this is equivalent to having P minus K linear constraints. And by linear constraints, what I mean is that we can find vectors Lj such that Lj transpose times B is equal to 0. Of course, we don't know necessarily those LJs, otherwise we could just rewrite our linear regression. And so this assumption that the rank of B is equal to K allows us to rewrite B transpose as U times V, where U is P times K and V is K times Q, and both are of rank K. And so this means that we have at most P plus Q times K regression coefficients to estimate. But we'll see later that it's actually a bit smaller because we have also, it actually imposes more constraints than this on the number of free parameters. So the main result that allows us to fit this sort of model is Brillinger's theorem. And so assume that xi and yi have mean 0, and define sigma y as the covariance matrix of the yi's, sigma x as the covariance matrix of the xi's, and sigma yx as the covariance matrix between the yi's and the xi's. And assume that sigma x is invertible. And finally, we also assume that we have P by P positive definite weight matrix capital gamma. And so the P times K and K times Q matrices UV of rank K that minimize this criterion here, so the trace of the expected value of gamma to the 1/2 times the outer product of yi minus uvxi times gamma to the 1/2 again. And so the matrices that minimize this criterion are given by gamma to the negative 1/2 times wk for u, and then for v it's wk transpose times gamma 1/2 times sigma yx times the inverse of sigma x. And so where here the columns of wk are the normalized eigenvectors corresponding to the k largest eigenvalues of this matrix here, gamma 1/2, sigma yx, the inverse of sigma x, the transpose of sigma yx times gamma 1/2 again. And so we can see here how to minimize this criterion. We end up having to solve an eigenvalue problem or an eigendecomposition problem. And so this is at the population level, this is the main result that allows us to estimate the reduced rank regression model. So I just want to make a few comments about this result. So first, so we won't prove this, but it's not too hard to deduce this from the Eckhart-Young theorem that we discussed in the lectures on PCA. A second observation or a second comment is that if we assume that P is less than or equal to Q and that we choose K equals to P, we actually recover the OLS estimate, because at that point if we multiply V hat transpose and U hat transpose, the WKs cancel out and we're left with the inverse of sigma x times the transpose of sigma yx, which is just the OLS estimator written in the population notation. The next comment is that we can actually recover canonical correlation analysis as a special case of this result. And so if for gamma we take the inverse of sigma y, and of course if we assume that sigma y is invertible, then the columns of U are simply the canonical directions for y. And finally, the last comment I want to make is that the term reduced rank regression is typically reserved for the case when gamma is the identity matrix. And so the weight matrix is just IP. But the level of generality allows us to create a framework where canonical correlation analysis, reduced rank regression, and multivariate linear regression are all special cases. And so this, of course, this was a result about the population quantities. And so since we have a random sample, if we translate this result at the sample level, we get the following. So U hat is equal to WK, V hat is WK transpose times Y transpose X times X transpose X inverse. And where the columns of WK are the normalized eigenvectors corresponding to the K largest eigenvalues of Y transpose X, the inverse of X transpose X, times X transpose Y. And so in other words, we can write our estimate for the reduced rank regression as follows, and we see that it's actually a transformation of the OLS estimator. So if B hat OLS is the least squares estimator, then B hat RR is B hat OLS times WK times WK transpose. And so let's look at an example. Since we motivate reduced rank regression through multivariate linear regression, I thought we could reuse the same data set. So recall the plastic film data, where we have 3 outcome variables, tear, gloss, and opacity. And we also have 2 covariates, so rate and additive, which are both binary covariates with 2 levels, so high and low. So first we fit the least squares estimator, and if we look at the coefficient, we have these quantities here. And so just recall that we can recover the same coefficient by using matrix multiplications. So if we select the three outcome variables and turn from plastic and then turn this into a matrix, which we call Y, and then if we do the same with X, and so we can use the model.matrix function to create dummy variables for the binary covariates. We see that we get the same as OLS if we do this operation here. So cross prod is x transpose, and so cross prod xy is x times y transpose. I apologize, I mean x transpose times y. And so solve will give us x transpose x inverse times x transpose y. And so beta OLS is this matrix product, and we see that we recover exactly the same thing as if we use the fit function. And so now let's do reduced rank regression. So recall that we have to transform the OLS coefficients by a matrix product that involves the eigenvectors of some matrix. So this matrix is cross prod of y and x, so y transpose x, times the beta OLS, so the estimate that we got from least squares. So we call this matrix M. We can compute its eigen decomposition, and we can extract the vectors. So let's start by assuming that the rank is equal to 1. And so we only select the first eigenvector of M. Here I add the expression drop equals false because I want to keep this as a matrix. If I don't have drop equals false and I select just one column, I'll get a vector instead of a matrix. Next, I add the column names of Y to the rows of W so that we keep track of the names of the outcomes. And next, we can get beta reduced rank regression as, again, a transformation of beta OLS, where we multiply by W transpose. And so if we look at what we get, we see that we indeed get a matrix of the same size, but the coefficients now are collinear. What I mean by this is that the each row is a scalar multiple of each other. And so for example, if I take the first row and I divide by the second row, you see that we get the exact same constant here. In this case, 359. Of course, one question you may have is, how do we select the rank k, which is the tuning parameter in this for this method? One approach is to use sequential inference, just as we did for canonical correlation analysis. I won't go over the details, but if you're interested, you can look at section 2.6 of the book by Reinsel and Velu on multivariate reduced rank regression. A second approach would be to choose a k that minimizes the cross-validated mean squared error, just like we did when we discussed regularized regression a few lectures ago. For this lecture, the method I want to discuss is a method based on information criteria, and in particular based on Akaike's information criterion, so AIC. Recall the general form. So if we assume a model, a distribution for the y's, Akaike's information criterion is defined as -2 times the log likelihood at the maximum likelihood estimates, plus 2 times d, where d is the number of parameters to estimate. So how do we select d? So if we restrict b to have rank k, there are actually only p plus q minus k times k free parameters. And here's how you can derive this. So remember, so we assume B as rank k, so this means that the column space of B has dimension k, and so we can find a basis of size k. So this gives us k times q free parameters, so k different vectors of length q. And now what we have to do is fill out the rest of B. So we have p minus k remaining columns, and for each of those columns, because they're we can express them as linear combinations of the first q columns, we only need k numbers. So the numbers, the coefficients in the linear expression, linear combination, those are the free parameters, and we need k of those for each of the p minus k columns. And so if we add k times q and k times p minus k, we get the expression above. So this is what we would call the naive definition for D, for the degrees of freedom. A more careful analysis based on Stein's unbiased risk estimation framework actually shows that this is an underestimate for the true degrees of freedom of the model. And here's how you would derive the true degrees of freedom using Stein's theory. Let lambda 1 to lambda p be the eigenvalues of the matrix we called M. So y transpose x times the inverse of x transpose x times x transpose y. Then D would be p plus q minus k times k, so the same degrees of freedom we had earlier, plus an extra piece, which is twice the sum of L from 1 to k, of the sum j going from k plus 1 to p, of lambda j over lambda L minus lambda j. And so if you want to see more details of how to derive this, you can look at this 2016 paper by Yuan Ming called Degrees of Freedom in Low-Rank Matrix Estimation. Just one note, so if you do reduced rank regression using the RRPAC package, the first type of degrees of freedom is called naive, and the second type is called exact. And by default, this function uses the exact degrees of freedom, so the one you would get from Stein's theory. So let's apply this to the plastic data. So first we're going to create a function that computes the reduced rank estimate. Here I just recopied the code from earlier, but I added the possibility of changing the rank. So instead of just having rank equals 1, which is the default, we can increase it as well. And to make sure that our function is computing the quantities it has to compute, or it should compute, we can check that red rank yx gives us back the same estimates we had earlier. So beta underscore RRR. So let's compute the AIC. So the first component is the log likelihoods. And so using the sapply function, I compute the reduced rank estimate for k, for the rank being equal to k, where k now goes from 1 to 3. Next, I compute the residuals, and then I get the log likelihood at the maximum likelihood estimates by using the dmvnorm function, evaluated the residuals on the log scale, and then the sigma matrix is the cross product of the residuals divided by n, and then I sum all of those values and I multiply by -2. So I get -2 times the log of the likelihood. So this is the first part. The second part again involves the degrees of freedom, and we'll start with the naive definition. So when we do this, we get these quantities here. For the AIC, we get 139, 133, and 126. And recall that we want to select the model that minimizes the AIC, and therefore we would select the full rank model here. Next, we can repeat this with the exact degrees of freedom. So here we have a function that computes this double sum and the function of the eigenvalues. So lambda j over lambda l minus lambda j. And we just have to also handle a special case. So if k is equal to the number of columns, we just return 0. Otherwise, we return twice the total, where total is this double sum. And so next, if we compute the AIC using this definition of the degrees of freedom, we get these values here. So 139.4, 134.9, and 125.9. And so again, if we select the model with the smallest AIC, we select the full rank model. So let's contrast this with the approach taken by the RRR function in the RRPAC package, which uses a different AIC that doesn't use the likelihood, the multivariate normal likelihood, but instead uses only the OLS criterion. And so perhaps if you don't believe your data follows a normal distribution, the RRPAC definition of AIC seems more natural or more robust. And so the way to use this function, we simply call RRR on y and x, and then we need to specify the type of information criterion we want. So in particular, I want the AIC. And you can look at the documentation if you want to see the different choices. And so when we do this, it selects the model with the smallest AIC automatically, and in particular, it selects the model with rank 1, so a different model than what our own AIC selected. Now let's look at a second example, which is the tobacco data set that comes with the RRR package. And so we have, we define those two matrices, tobacco underscore y and tobacco underscore x. X would be the covariates, and we see we have 6 covariates and 25 observations. And tobacco underscore y would contain the outcome variables. And we see that we have, of course, again, 25 observations, but 3 outcome variables. So we can run the RRPAC function from the RRPAC package on tobacco y and tobacco x with the default settings. And once again, for this particular model, the estimated rank is 1. And so we can visualize the coefficients using the level plot function in the lattice package. And we can see this graph here. So we can see that the largest effect that the covariates have on the outcomes happen on the percent sugar outcome variable. And in particular, the largest positive effect comes from phosphorus, which is the teal blue, or the, I guess it's, you can also call this cyan, so the darkest cyan color here. And on the other hand, the largest negative effect comes from the nitrogen covariate, which is the darker magenta color. And if you look at the other outcome variables, because the estimated rank was 1, we would expect those columns, or those rows, to be scalar multiples of the middle row. And you can also see that the effect are in the same directions, and so the scalar factors would be positive in this case.